In the previous lecture, we learned about real vector space and some examples. So recall the definition of real vector space again. That would be useful in today's lecture. So what's a real vector space? A non-empty set V is said to be real vector space if two operations denoted by plus and dot are defined such that for all UVW belonging to V and AB belonging to R, 10 properties are satisfied. 5 properties with respect to plus or vector addition, and 5 properties, you can say mixed properties with respect to dot scalar multiplication. So what are these properties? U plus V belongs to V means V is closed with respect to vector addition. U plus V equal to V plus U, commutative property with respect to addition. Third property is associative. Fourth means 0 belongs to V. Additive identity exists in V. U plus 0 equal to U equal to 0 plus U. Fifth property implies additive inverse of each element in V exists. So minus U denotes additive inverse of U. With respect to scalar multiplication, there are 5 more properties. A dot U belongs to V. A dot U plus V equal to A dot U plus A dot V. Next, A plus B dot U is A dot U plus B dot U. Ninth property, A B dot U is A dot B dot U. And 10th, 1 belongs to R. 1 is a real number such that 1 dot U equal to U. From the examples, now you know that these plus and dot may have any definitions. Okay. Plus is vector addition, dot is scalar multiplication. So V is vector space if these 10 properties are satisfied. 5 properties with respect to vector addition and 5 properties are shown here. Okay. After that we did some examples. Now let's see what is a subspace. If W is a subset of a vector space V such that W is also a vector space under the same operations as in V, then W is called a subspace of V. Subset of V which itself forms a vector space under the same operations as in V is a subspace. See this example. This set W equal to x1 comma 0 where x1 belongs to R is a subspace of R2. Why? You can verify the 10 properties in W. It forms a vector space. What is the difference? This second entry is 0 in R2. What kind of entries are there? x1 comma x2 type or x1 comma y1 type, where x1 y1 are real numbers. Second entry is 0. Okay, so naturally W is a subset of R2. So you can verify that all 10 properties are satisfied. So it is a vector space because it is a subset of R2, so it's a subspace of R2. To verify subspace, it is enough to verify 2 properties. Instead of verifying 10 properties independently in W, verify 2 properties. What are those? Verification of vector addition and scalar multiplication is sufficient. Why? Because of this theorem. A subset W of a vector space V is a subspace of V if and only if W is closed with respect to vector addition and scalar multiplication. Means verify only two properties. UV belonging to W, A belonging to R implies U plus V belongs to W and A dot U belongs to W. Verifying these two properties is equivalent to verifying the 10 properties according to this theorem. So it's very important. If you show W is closed with respect to vector addition and scalar multiplication, it is subspace of the vector space. Okay. So let's see how we can show that W equal to this is subspace of R2. Choose two members from W. Say U equal to x1 comma 0 and V equal to y1 comma 0. Okay, in the notations, if you want to show here x1, x2, it's fine to avoid the confusion. In R2, so one member is x1 comma 0, other is y1 comma 0. So what is u plus v? It is x1 plus y1 comma 0 by definition of vector addition in R2. It belongs to W again. Why? Because first entry is a real number, second entry is 0. This kind of members are there in W. So it belongs to W. Likewise, you can check u dot a dot u means ax1 comma 0. This also belongs to W. So W here is closed with respect to vector addition as well as scalar multiplication. So it is a subspace. You can see the solution here also. Now let's do these examples of verification of subspace. Verify whether W equal to xy, again it is a subset of R2. What kind of xy are there in W? X minus y is 0, where xy belong to R. Means all ordered pairs xy, where x minus y is 0, belong to W. Is it a subspace of R2? That is the question. Is it a subspace of R2? So again you have to show two properties, vector addition and scalar multiplication. So choose two members from W, x1 y1 and x2 y2. Suppose these two belong to W. Okay, these two belong to W. And choose a real number also, A belongs to R. So what is the addition of these two? By definition of vector addition in R2, it is x1 plus x2, comma y1 plus y2. Question is that whether this belongs to W again or not. It belongs to W. Why? Because x1, y1, x2, y2 belong to W, so x1 minus y1 is 0 and x2 minus y2 is 0. Here, let's solve the difference of these two. What do we get? x1 minus y1 plus x2 minus y2. Correct? 0 plus 0. So it is 0. So difference of the two entries is 0. That's why it belongs to W. Same way, if we solve a dot x1 comma y1, what do we get? x1 comma ay1. What is the difference of these two? ax1 minus ay1, that can be written as a times x1 minus y1, a dot 0, a into 0. This dot is different from that one. Anyway, a, this is product of two real numbers, 0. So this belongs to W. Any member in W is an ordered pair where the difference of two entries is 0. Right? So we verified these. It means W is closed with respect to vector addition as well as scalar multiplication. So it is subspace of R2. Okay, so you need to note down the characteristic of the members in the given set W. Accordingly, you need to verify the properties. Next example, verify whether the W which carries the ordered pairs where second entry is square of the first entry, y equal to x square. Is it a subspace of R2? Is it a subspace of R2? You need to verify only two properties. If any of the properties fail, then it is not a subspace. Do you think that both properties are satisfied? See, vector addition is not satisfied in this example. 1 comma 1 belongs to W. Why? Because 1 square equal to 1. And 2 comma 4 belongs to W because 2 square equal to 4. Correct? What is the sum of these two? Both these are members of W. Sum of these two is 1 plus 2, 1 plus 4 means 3 comma 5. Do you think that this belongs to W? No. Because 5 is not square of 3. So you see, the vector addition property is not satisfied. Closure property with respect to vector addition is not satisfied. So you need to give one counter example to show that a property is not satisfied. It means it is not a subspace of R2. Next, verify W which carries 2 cross 2 order matrices such that, what is this? Determinant of this, PS minus QR, means non-singular 2 cross 2 matrices is a subspace of M22. Is it a subspace of M22? M22 means the vector space of all matrices of order 2 cross 2. In this case, the matrices with determinant non-zero are collected. 2 cross 2 matrices with determinant non-zero, non-singular 2 cross 2 matrices are collected in W. Is it a subspace of M22? No, it is also not a subspace. Why? Because 1 0 0 0 1 0 0 1 and minus 1 0 0 minus 1 both are members of W, because determinant of this is 1 and determinant of this is also 1. Determinant, both these are non-singular matrices of order 2 cross 2. What about their sum? Sum is 0 0 with the null matrix 0 0 0 0. This does not belong to W. Okay. So vector addition property doesn't hold here, means it is not closed with respect to vector addition, so it is not a subspace. Okay, now some algebra of subspaces. Let W1 and W2 be two subspaces of a vector space V. Show that intersection of these two is also a subspace of V. means intersection of two subspaces is again a subspace. How to prove it? Again, if you want to show some set as subspace of the vector space, you need to verify two properties. It is closed with respect to vector addition and scalar multiplication. So choose two members from W1 intersection W2. Then you would like to prove that U plus V belongs to W1 intersection W2, and also if A is any real number, then you would like to show A dot U belongs to W1 intersection W2. Okay? But before that, you also need to tell that W1 intersection W2 is non-empty. Otherwise, you cannot choose members. So, do you think that W1 intersection W2 is non-empty? Yes, it is non-empty because both are subspaces, both are vector spaces. So, at least the additive identity belongs to both the subspaces. So 0 belongs to W1 intersection W2. So W1 intersection W2 is non-empty. We can choose members from it. Okay. Now UV belong to W1 intersection W2. That means U comma V belong to W1 as well as these belong to W2. But W1 is a subspace. So U plus V belongs to W1. Likewise, U plus V belongs to W2. What does it mean? U plus V belongs to W1 intersection W2. These I have written because W1, W2 are given as subspaces of the vector space. So finally, U plus V belongs to W1 intersection W2. What does that mean? W1 intersection W2 is closed with respect to vector addition. Same way, you can show the closure property with respect to scalar multiplication. A belongs to R, U belongs to W, A dot U belongs to W1. Why? Because W1 is subspace. A dot U belongs to W2, again because W2 is a subspace. This means A dot U belongs to W1 intersection W2. So proof is simple. Intersection of two subspaces is a subspace. But union of two subspaces need not be subspace. Think some example to show this. It's a very good example. W1 which carries ordered pairs with second entry 0 is a subspace of R2. You already know it. Likewise, W2 0, x2 type entries or 0, x2 type members where x2 belongs to R. It is also a subspace of R2. But their union is not a subspace. Why? See, 1, 0, 0, 1 belong to W1 union W2. Can I say this? Yes, 1, 0 is a member of W1, 0, 1 is a member of W2. Naturally, these two are members of W1 union W2. But what is the sum of these two? 1, 1 that does not belong to W1 union W2. Because any member in W1 union W2 carries ordered pairs where either first entry is 0 or second entry is 0. So closure property with respect to vector addition is not satisfied. So W1 W2 are subspaces of R2, but W1 union W2 is not a subspace. So when the union can be subspace, the condition is either W1 is subset of W2 or W2 is subset of W1. Its proof is given in the lecture notes, you can see there. Proof is easy. So intersection of subspaces is a subspace. Union need not be. Union is subspace only when one of the subspaces is subset of the other. Okay. Next, a very important definition, span of a set. What is span? The set of all linear combinations of finite number of members of a subset S of a vector space V is called the span of S and is denoted by span S or LS. We will be using this definition more commonly, LS. LS means linear span of S. So what is it? It is linear combination of finite number of members of S. Here A1, A2, An, etc. belong to real numbers and V1 to Vn are members of S. So if you construct all finite linear combinations of the members of a given set S, then the collection of such linear combinations gives linear span of S. See this example. What is linear span of this set? S equal to 1, 0 and 0, 1. S carries two entries in R2, 1, 0 and 0, 1. So what is LS? Multiply first vector by some scalar A, some real number A, 1, 0 plus B into 0, 1, where AB belong to R. So this set gives linear span of S because you have written all possible linear combinations of the members of S. You can simplify it further if you like. It is A comma 0 plus 0 comma B. After addition you get A comma B, where AB belong to R. If you see it carefully, it is nothing but R2, the whole vector space R2. So linear span of this set is the whole vector space R2. Okay. Now what is span of this set R3? Again, you will write LS equal to A times 2, 3, 4, B times second vector, C times third vector. What do you get? You get this expression. It is fine. This is the linear span of S. But if you want to identify in terms of some known set, then find simplified span. For example, here we are able to identify that this set is R2. Okay. But here we are not able to see it clearly whether it is R3 or not. It may be subset of R3 also. Okay. But it is also possible that this set represents the whole vector space R3. So how to do that? Using simplified span. What is simplified span? You write these vectors in a matrix and find its RREF, reduced row equivalent form. After that, find the linear span. Because span of this set and the row equivalent matrix, if you consider, and the row vectors, then a linear span of both are same. Alright. So this is the way to get simplified span. If you write simplified span, then it's easy to identify what is the linear span. So its RREF is this matrix, and from this we can see A times first row plus B times second row, C times third row vector. Then we get exactly R3. So for simplified span, what to do? Find RREF. In case of R3, R4, etc. In case of Rn, you can say. Write the vectors as rows of the matrix, find RREF, and then write the linear span of the row equivalent matrix that you get in the end in RREF. For polynomials also you can apply the similar strategy. In polynomials, what to do? Write their coefficients. For example, here the first polynomial is x power 3 minus 1. So what are the coefficients? For x power 3, 1, x square and x are missing, so write 0 for them. Same way for the second polynomial and third polynomials. After that, find its RREF and then write the linear span. That would be simplified span. Okay. In polynomials, you know the coefficients play the role. So just write the coefficients in order, find RREF and then write the linear span. So it is simplified span of this set in the vector space R3. In the vector space P3, the polynomials of degree less than equal to 3. Next, S is the set of matrices of order 2 cross 2. So in this case also you can find simplified span. Instead of dealing in the form of matrices as it is, write the first matrix as row of the matrix minus 1 1 0 0. Okay. Second matrix 0 0 1 minus 1. Third matrix minus 1 0 0 1. Find its RREF, write the matrices back and then the linear span. So with the set of matrices also you can deal like this for finding simplified span. Okay. If you don't want to write simplified span, just simply multiply the given vectors by ABC and add them. Whatever you write after the calculation, that is the linear span of the given set. But for simplified span, this is the way to do the calculations. Span of the empty set is defined to the singleton set containing the 0 vector. This is convention. So L phi is the set carrying 0 vector. Now if S is subset of the vector space V, then Ls is a subset of V. Why? Ls is a subset of V. Say S carries n vectors V1 to Vn. So what is Ls? Ls carries linear combinations of these vectors A1, V1 plus and so on, A and Vn, where AI's belong to real numbers. It is S is subset of V, it is given. Ls is also subset of V. Why? What is A1, V1? A1 dot V1 you can write. This belongs to this belongs to V or not? Yes, because of the property of scalar multiplication. Likewise, A2, V2 belongs to V. So addition of two vectors in V again belongs to V because of the property of vector addition, closure property with respect to vector addition. So repeated application of scalar multiplication and vector addition properties gives that this whole expression belongs to V again. So linear combination of members of S again belong to V. That's why Ls is a subset of V. Ls is a subspace of V. For subspace it's very simple. Choose two members from Ls. Choose two members from Ls. Say you choose U equal to A1, V1 and so on, A and Vn. Another member V equal to B1, V1 plus and so on, B and Vn. Both these are members of Ls, correct? What about U plus V? It belongs to Ls again or not? What is U plus V? A1 plus B1 times V1 plus and so on, an plus bn times vn. It belongs to ls because it is again a linear combination of the members of S. Real plus real is a real again. So it is a linear combination of the members of S V1 to Vn. So it belongs to Ls. Likewise, you can check A dot U belongs to Ls. So both properties of subspace are satisfied. That's why Ls is a subspace of V. Ls is the minimal subspace of V containing S. How to show this? If W is any subspace containing S, then Ls is subset of W. That means Ls is minimal subspace containing S. W is any subspace containing S. Ls already carries S. Do you think so? Ls already carries S? Yes, because if I choose A1 as 1, other scalars 0, then the whole combination gives me V1 and it belongs to Ls. Or can say, write it like this. Suppose V1 is given. V1 is a member of S. V1 I can write 1 into V1 plus and so on, 0 into V2 and so on, 0 into Vn. It is a linear combination of members of S, so it belongs to Ls. So V1 is a member of S, it goes to Ls, likewise V2, V3 and so on. So S is subset of Ls. W is any subspace containing S. We have to show that Ls is contained in S. So this shows that Ls is minimal subspace containing S. So how to show this? Pick a member from this and show that it belongs to W. So it's very simple. If V is any member of Ls, then V should be linear combination of members of S. And linear combination of members of S goes to W. Why? Okay, let me write it separately. V is a member of Ls. So what is the format of V? V is of the form C1 V1 to Cn Vn. Correct? Now this belongs to W. That is the claim. Why does it belong to W? Because this is a linear combination of the members of S. And S is subset of W. Further, W is a subspace, so this linear combination goes to W. Okay, so the argument is very simple. So Ls is the minimal subspace of V containing S. Next, a very important concept, the concept of linearly independent vectors. I have already introduced you the concept of linearly independent row vectors in chapter 1. So hope you recall that one. It's similar to that. Now we are talking in general, any vectors in the vector space. A subset S equal to V1 to Vn of a vector space V is said to be linearly dependent if there exist real numbers A1 to An not all zero such that the combination is 0. If S is not linearly dependent, then that is the linear combination of the vectors equal to 0 implies only one solution, that all the scalars are 0. In this case, S is linearly independent. In simple words, you can remember this. If we are given n vectors in a vector space, then put their linear combination 0, 0 vector, If solution of this is only 1, means it implies that all the scalars are 0 only the trivial solution, then the vectors are linearly independent. Otherwise, the vectors are linearly dependent. Okay, so you can recall that it is similar to the concept that I told you in chapter 1 regarding linear independence of row vectors of a matrix. So instead of row vectors, now here these are any vectors in the vector space V. See this example, S equal to 1, 0, 0, 1 is linearly independent in R2. You have to show this. So how to show? Put the linear combination of the two vectors equal to 0. What is 0 vector in R2? 0, 0. Solve this for A1, A2. If you get only one solution, 0, 0, then the vectors are independent. So if you simplify it further, what do you get? What is the left hand side? A1, A2. This is left hand side calculation, right hand side is 0, 0. From this, what do you get? A1, 0 and A2, 0. That means the vectors are linearly independent. This you can verify yourself that 1, 2 and 2, 4 are linearly dependent. Why? If you go in the same manner, you will have infinitely many solutions in this case. You have done it earlier, okay? Otherwise also I can write a combination which gives 0 vector but at least one scalar is non-zero. What is that combination? I can put here -2, correct? Here the scalar is 1. Both the scalars are non-zero. We need only one and the combination is 0. So you have found a combination where scalars are non-zero and the overall linear combination of the vectors is 0. Vector, that means the vectors are linearly dependent. Okay. How to check these three vectors are linearly dependent in R3? Same way. A1 into first vector, you can use ABC as per your convenience. A times first vector, B times second vector, C times third vector. Put that combination equal to 0, 0, 0. Because the 0 vector in R3 is 0, 0, 0. After that, you will have homogeneous system in 3 variables. Solve that. If you get only trivial solution 0, 0, 0, then the vectors are linearly independent. If you get infinitely many solutions, then the vectors are linearly dependent. Okay. Two vectors in a vector space are linearly dependent if and only if one vector is scalar multiple of the other. This is a good result because checking two vectors for linearly independence is very easy because of this. Just you need to see whether the two vectors are scalar multiple of each other or not. So if the vectors are scalar multiple of each other, then those are dependent. You can see in this example itself, 1, 0 is not scalar multiple of 0, 1, whatever scalar you use. You cannot write 1, 0 equal to some scalar into 0, 1. For any scalar, it is not possible. Correct? That's why these are independent. But in the second case, this example, 2, 4 can be written as 2 times 1, 2. So these are dependent, linearly dependent. Now these are some very simple results but are important. A finite set S containing at least two vectors is linearly dependent if some vector in S can be expressed as a linear combination of the other vectors in S. Proofs are given in the lecture notes, you can see there, but try to understand the logic here. S is the given set, say it carries n vectors. S is linearly dependent or independent means the vectors are linearly dependent or independent. So S is linearly dependent if and only if some vector in S can be expressed as a linear combination of the other vectors in S. Say V1 can be written as linear combination of the remaining vectors B2, V2 and so on, Bn, Bn. Okay, so at least with this vector you are seeing 1. You can put it on the right hand side. You can write it like this, plus minus 1. In this case, V1 is linear combination of the remaining ones, but this combination shows you that, this expression shows you that the overall combination is 0 where one scalar is confirmed non-zero. What does it mean? The vectors are linearly dependent. So proofs you can read from the lecture notes. I think those are very simple. I need not to go into the details here. Next theorem. A non-empty finite subset S of a vector space V is linearly independent if and only if every vector V belonging to LS, means the linear span of S, can be expressed as a linear combination of the members of S, can be expressed uniquely as a linear combination of the members of S. Both ways you can prove this result easily. Say, consider the left hand side, or you can say the left part of this theorem. S is linearly independent. Start with this and show that any vector V in LS can be expressed uniquely as a linear combination of the members of S. So S consider the same set with n vectors. You are saying that it is linearly independent. What is to be shown? That any member in LS can be written as uniquely as a linear combination of the members of S. Say it is not written uniquely. Say you have two combinations, A1 V1 to AN Bn, and another combination is B1 V1 to Bn Bn. Uniquely means these scalars cannot be different. I have written two different combinations. What I get if I subtract the two? 0, A1 minus B1, V1 plus and so on, AN minus Bn Bn. What does it mean? 0 I have written on the left side. Linear combination of the vectors V1 to Vn is 0, and these vectors are linearly independent. That means all these scalars must be 0 by definition of linear independence. But from this you get that A1 equal to B1, A2 equal to B2, AN equal to Bn. It means V can be written uniquely as the linear combination of the members of S. Same way you can do the other side. Okay, proof is given in the lecture notes. So this proofs of all these theorems in this part is very simple, just you need to read it once. Any set containing 0 vector is always linearly dependent. In these vectors, say 0 is included. It is always linearly dependent. Why? Because whatever combination you consider, with 0 at least I can put some non-zero scalar. Say I put 1 into 0. Whatever these are, okay, let me put this 0. This is a linear combination of the members of S where one scalar is non-zero. The whole linear combination is 0, correct? But the scalar with 0 vector is non-zero. That means these vectors are linearly dependent. So any set containing 0 vector is linearly dependent. Now next is the definition regarding infinite subset of the vector space V. When we say it is linearly dependent, if it's every finite subset is linearly dependent. If every finite subset of an infinite subset of the vector space V is linearly dependent, then that set is linearly independent. So this set S equal to 1 comma x square and so on is infinite linearly independent set in P, because whatever finite linear combination you consider, say a0 into 1 plus a2 into a1 into x plus a2 into x square and so on, an x power n. This can be 0 only when all these coefficients are 0. Okay. So every finite subset of S in this case is linearly independent. So this is infinite set, but it is independent because its every finite subset is linearly independent. So this is the definition of infinite linearly independent set. Okay. So we have covered the topics up to linearly dependent and independent sets in a vector space. So what do you need to know? The theorems that I have discussed, you need to look at the proofs from the lecture notes and practice problems from the textbook. Okay, so we'll meet in the next lecture. Thank you.